Hi there, welcome to a new physics lesson for adventure and discovery. Today, our topic is converging lenses. We're continuing our look at optics, how we can use light and manipulate it using mirrors and lenses, and today we're finally going to get into lenses, which is really cool. And we're going to talk about our first type of lens, what we call the converging lens. And so let's jump into this. We're going to talk about what are lenses, what makes a converging lens a converging lens. We're going to take a look at the parts, and how it applies to the lens equation and the magnification equation we learned a couple days ago. And then we're going to take a look at how diagrams are a little bit different for these lenses, especially for converging lenses. And there's like three different scenarios for converging lenses. Converging lenses are kind of like concave mirrors where there's different scenarios that can happen when we're drawing our ray diagrams. Okay, so it's pretty fascinating, and let's jump into this. So converging lens is a lens in which the light rays converge on each other, or notice in this picture on the right here, picture A, when light travels through this lens, it travels through it and it converges, it kind of focuses on a certain point. That would be a converging lens, as opposed to a diverging lens. So here on the left, we have a diverging lens that makes a light split up. Okay, so diverging lens and converging lens. Converging lenses are also called convex lenses, because if you notice, this curve is bulging out towards you. It's not concave, it's a convex. So a convex lens, the light enters through it parallel, and then it focuses on a certain focal point. But here's the interesting thing about convex lenses. Convex lenses actually have two focal points. They'll have a focal point in front of the lens and also in back of the lens. So that's kind of what defines it. And so applying our lens equation as well as the magnification equation to this, notice it's the same as when we're working with mirrors. We have 1 over p plus 1 over q equals 1 over f, which is the focal length. Or just as a review, p is distance from the actual object to the lens, q is distance from the image of that object to the lens, and then f is the focal point. Okay, and make sure they are all in meters. And same thing for the magnification equation. It's the same equation that we're using, except now it's applied to lenses. We have magnification equals the height of the image over the height of the object, or in other words, the negative distance from the image to the lens over the distance of the object to the lens. And again, just like mirrors, if that magnification is positive, we will end up with a virtual enlarged image, and if the magnification is negative, the image will be flipped upside down and real. In this case, a real object will appear on the opposite, on the opposite side of the lens. We'll be able to see it through the lens. That would be the real object. In terms of a virtual image, a virtual image for a lens would be on the same side as the object. So it's different. It's almost opposite that of mirrors. So here's our sign convention, and it's pretty much the same thing, right? If the p is positive, it's going to be a real object. It's going to be in front of the lens. Vice versa if it's negative. Q image is going to be real if it's positive and in back of the lens. So here's the difference. It's going to be in back of the lens. If the image is negative, then it's going to be a virtual image in front of the lens. Focal length. Here's the kind of thing that separates it between a converging lens and a diverging lens. If the focal length is positive, it will be a converging lens because the focal length is in back of the lens, it's through the lens. If the focal length is negative, then that means that the lens that we're working with is a diverging lens. Okay, and then same thing for image height, we kind of just went over that. Positive height is upright. If it's a negative height, it's upside down. And then magnification, if it's positive, it's a virtual image, and a negative, it's a real image. And so onto ray diagrams. Ray diagrams are almost the same as mirrors, and so we don't have to memorize a whole new set, but here's kind of how that works. So for lenses, we're going to start off with the object, just like mirrors, and we're going to draw a straight arrow through the object, from the object to the lens, parallel to the principal axis. Once it hits the lens, it's going to go through the opposite focal point. Okay, the key word here is opposite. It's going to go through the lens to the opposite focal point. The second arrow will go through the near focal point and then parallel to the principal axis once it goes through the lens. And then the last one, and here's the difference, instead of the center of curvature, we're going to just draw a line straight through the center of the lens to the object. All right, so how does that work? Here's an example of that. Let's say I have this red arrow. My first arrow is going to be parallel to the principal axis from the object to the lens, and then through the, notice it's the focal point on the opposite side of the lens. Okay. My next line, this is the third line actually, goes straight through the center of the lens. And then my last line goes through the near focal point and then parallel of the principal axis. So notice where the three lines converge, that's where my image is going to be. It's going to be upside down and smaller than my real image. Okay, but just like we talked about in concave mirrors, convex lenses have a couple of scenarios that happen when we have these different ray diagrams. Also here, notice this it's going to be a real image, smaller and upside down. So when we have an object between the second focal point, or 2 times the focal point, which is not the center of curvature anymore because this is not a curve, but if we have something between that and the near focal point, notice that, okay, we're going to do the same thing. So it's going to go through parallel and then through the focal point. We're going to have one going through the center of curvature. Notice if it's between these 2 points, our image is going to be real and it's going to be enlarged. Still upside down, but enlarged, which is going to become important in just a few minutes. If my object is inside the focal point, so notice through parallel and then through far focal point, through the center of curvature. Notice if it's in front of the focal point, my image will actually be not through the glass, but it's going to be in back of it. It's going to be a virtual image and it's going to be upright, also enlarged. But that's if it's inside the near focal point. Notice we can't draw that second arrow because it's in front of the second focal point. Okay, so this would be a good example of like a magnifying glass. If we have a magnifying glass and you look at it carefully, it's really a convex lens. It's a lens that bulges out towards you. And so when you hold up a magnifying glass and you look at something through the magnifying glass, the object appears way bigger. And the reason for that is because we're looking at it in front of the focal point. The image is going to be on the same side as that object. Okay. And so to sum up, here the same rules as convex mirrors. We have 2f equals the center of curvature. Notice that converging lenses, just to sum up, it can produce real and virtual images. Okay? When it's outside of the focal point, the image will be real and inverted, it will be upside down. However, if it's inside of the focal point, like the magnifying glass, if you hold it really close to an object, the image will be virtual and upright. It won't be flipped. Okay, when it's outside of that when it's inside of that 2f, the image will be larger than usual, than real life. But when it becomes farther away, as you move the magnifying glass farther and farther and farther, it's going to get smaller and smaller and smaller, and eventually it'll flip upside down. All right, so take a look at your packet. I have all those different scenarios in your packet. You'll be practice as much as you can. And so thanks so much for joining us, and we'll see you next time.